Hi, and welcome back. During the course of the sessions this morning, we've heard about, by name at least, the work of Swirlds and Ping Identity. And as we come to the last two sessions today, we're actually going to hear more about what they're actually doing. So I'm really pleased to welcome Leemon Baird, who's the founder of Swirlds, to talk more about what Hashgraph is and its appropriateness in this environment.
Well, thank you. Good afternoon. So we have had some talk. Yes. Can you hear me? That is much better. Okay. So we have had some talk today about Swirlds and Hashgraph, and I just thought you might be curious what it is, and I'll just go through it and show you what is going on with that and some of the interesting properties that it has. We've had now 7 talks in this room, the last 7 talks about how you might do identity things with a public ledger, why distributed consensus might be a useful thing, and what the limitations would be, and all sorts of very interesting things. I've enjoyed the last 7 talks. So I'm not going to talk very much about why you might want to do various identity type things on top of a distributed consensus system. But just for concreteness, let's pick one random example. Suppose you wanted to do distributed session management. So the IDP puts a session into the ledger when you authenticate to them, and then you're able to get into RPs, and then if the IDP ever discovers there's a problem with you, they turn off your session. They can revoke it. They can end it. You can do session logout. Or imagine the future where maybe there's multiple IDPs involved. Maybe for additional security, you have to log in or authenticate to several IDPs. They jointly somehow create this session, and then you're able to get into your bank or wherever. And maybe we're talking about continuous authentication, where these IDPs are constantly saying, yes, keep the session going, or no, I'm starting to be suspicious. In such a system, we have so many players talking to each other continuously that we actually start needing a ledger. We actually need something other than just a database inside my single IDP. And so I'm envisioning that kind of a system. We've got multiple parties that are coordinating with each other, and they're all communicating with each other, and we have to make sure that everyone gets the message and that everybody knows that everyone gets the message and so on. So this is what we're talking about, the future, moving towards a world where we're going to have more complexity in what's going on, and there actually becomes a need for this ledger. So what's a ledger about? Well, it's about broadcast. The main thing is that I got to be able to get information out. When I create a session, it needs to go out to everybody whom I might log into, all the RPs that I might log into. So it is very important that we have the ability to broadcast. But not just any broadcast. We need to be able to do reliable broadcast. I need to make sure that when I send out a session logout command, that everybody hears about it and logs out this session. If I discover that an attacker is trying to use this session, I need to tell the bank right away, please close down the session and stop giving away money to this person that I said was authenticated, if I'm an IDP. So we need to have reliable broadcast where people get the message. Not only do we need that, but we're going to need consensus reliable broadcast. So we're going to be having maybe multiple IDPs deciding to start your session or deciding to do continuous authentication and keep your session going. There's coordination between them. The community as a whole needs to come to the consensus as to whether your session is still continuing. It would be very strange if some RPs think your session is still going and some think it's not, and there's a difference of opinion. So we really are talking about consensus. So we need consensus reliable broadcast. And in addition to that, we'll need an immutable consensus reliable broadcast. Even in this example, sessions are short-lived, they don't matter. But you know, we may later need a record of this so that when the person steals $1 billion from the bank, you can say as an IDP, you know, I did tell the bank to shut down the system. It wasn't it wasn't my fault. And you need to be able to prove to the court, I did actually send out this message. So I'm going to need receipts, cryptographically strong receipts saying, yes, I did put this into the ledger, that I had this session logout request. And in fact, if we can get the bank to put a receipt when it reads it, that's even better. So we need receipts at both ends. Receipts of proof that you sent a message to the world and proof that the bank actually read, the RP actually read the message that was sent to the world. And in fact, we might not just need these receipts, we might need timestamps on these receipts. the community as a whole will agree on when I sent that log out and when the bank transferred the $1 billion, and the community as a whole then will have indirectly said which one happened first. And so we may need consensus on these timestamps. So these are some of the things that you might want in a consensus system. And you don't need it for cryptocurrency. You don't need it for some of the apps that are going on right now. This is for future things. It will be useful in the future to have immutable consensus, reliable broadcast with cryptographic receipts of sending messages and of receiving messages and consensus timestamps that are also digitally signed so we can show it to a court. So this is kind of the world that we're talking about here, some of the properties we might want to have. Now, we've talked a lot about blockchain and Hashgraph, and it is not true that blockchain is bad and Hashgraph is good, but what it is the case is that Hashgraph has some properties that are appealing that you don't have in blockchain, and so in some ways it may be the next step beyond blockchain. So let's talk about this. In both cases, the whole point is to make a ledger of transactions. We want to record transactions that various people in the community do, like creating a session or logging out a session. And we want to have the order of those decided by the community. And so we put them together, bundle them together into containers. In blockchain, they're called blocks. A block is a set of them. In Hashgraph, we call them events. But we have these containers of transactions. And in blockchain, not surprisingly, you get a chain of them. The community comes to a consensus on a sequence of these blocks, and then the sequence of the transactions is whatever sequence the blocks were in. So you look at the sequence of the blocks, you look inside of them and see where the transactions are, and that tells you the sequence of the transactions. Now, it's very important for blockchain that it is a chain. It is a single tree trunk. But you know what? If two different miners were to try to put on a block at the same time on the top of this chain, then my chain would fork, and it would no longer be a chain, and this would be bad. And so what blockchain does is the community decides, anytime that happens, the community decides which of the two to chop off and which one to keep so that it stays a chain. And so somebody used their supercomputer and lots of electricity over the course of who knows how long to mine one of those two blocks, and then it gets thrown away and they get no benefit. So there is some wasted effort here. There's inefficiency here. But we are going to have the community decide when to chop off blocks. And that's why this tree trunk on the left has lots of little limbs coming out that have been chopped off. It's a single line because we chopped off all the branches. Now in the Hashgraph, we simply allow branching. You branch all the time. And then we weave it back together into a single structure. So no block is ever lost. We call them events, but no event is ever lost. We never throw anything away. There's no wasted effort there. So that's nice. But it has another implication. In blockchain, when two people add on at the same time and we get this fork, the community is going to take some time to decide as a community and reach a consensus on which one to extend. Basically, everybody extends the one they think is longest. So it's going to take a little while. We need to make sure it doesn't keep branching while we're trying to figure out the first branch. You have this hydra that keeps growing heads faster than you can cut them off. This would be a bad thing. And so we have to slow it down on purpose. That's what proof of work is for in blockchain, is to intentionally slow it down. The only way to add a block is to solve a math puzzle that is so hard that on the entire planet, Bitcoin only has one person every 10 minutes solving it. And the whole purpose of that is to slow it down so that the community has time to prune a fork before the next fork comes. In Hashgraph, since we don't mine forks, then there's no need to slow it down. And so essentially, every person can be generating 100 blocks a second, and it doesn't matter. And so you can end up with a greater efficiency because you're not throwing anything away, but also greater efficiency in the sense that you don't need a supercomputer and you don't need electricity. You just run the algorithm, and you can run it on your cell phone. You know, it's not a hard algorithm to run. You don't have to waste time to try to slow people down artificially. And there are lots of other approaches to slowing people down, and we can talk about those. But in Hashgraph, the approach to slowing people down is don't. That's our approach to slowing people down. You don't have to. So that's the difference between the two. Hashgraph then ends up giving some properties that are interesting that we haven't really talked about in the community in the past, especially fairness. So the community is going to reach an agreement on the ordering of the transactions. And for a cryptocurrency, that's all you really care about. I just need to make sure that everybody agrees on what order these transactions happen, so that if I double spend a coin, everyone agrees on which of the two came first and counts, and which one came second and doesn't count. I don't really care about the fairness of which one we decide on as a community. If two happen about the same time, I don't really care which of the two the community puts first, but I have to make sure that the community reaches an agreement on some ordering of the two. For a cryptocurrency, that's all you need. For a stock market, you need more. If you wanted to actually do a stock market on top of a ledger, where you're putting in your bids and asks, you're saying, I want to buy this share at this price, and someone else is saying, I want to buy this share at this price, then it matters a lot who came first. And stock traders care a lot about getting their transactions happening quickly. They'll spend who knows how many millions of dollars, and I can give you numbers on that, trying to get a few milliseconds faster. They care a lot about who is first. And in existing systems like blockchain, where the miner can decide whether or not to put in an event or a transaction into his block. And if he doesn't put it in, then you have to wait another 10 minutes for somebody else's block. Or he can decide what order they go in the block. And in other systems that are based on leaders, the leader gets to choose the transaction, or he can arbitrate the order of the transactions, or he can arbitrarily delay some transactions. Maybe if you slip him a few dollars under the table, he'll be nice enough to put yours first. In a stock market, I know that wouldn't happen, so not an issue. Nobody would bribe them to do it faster. So what we care about here is fairness, which is a new property that people really haven't cared about in the applications that have been done in the past, but we've added this in. And so we have other things that are interesting, like Byzantine fault tolerance, and it's provable. You know, in blockchain, you never actually know that your transaction is for sure in the chain. It's just every time a new block comes out, you become a little bit more sure, and you go asymptotic to certainty. And so we say, well, you get 6, and that's pretty good. You're probably pretty sure after 6. But here it's different. You reach a point in time where you have a mathematical proof, yes, my transaction is in the ledger, and here's the exact point it was in history. And the exact point in history is the community consensus on where it should have been in history. And it's efficient, inexpensive, time-stamped, DOS-resistant, non-permission. Okay, so we have all of these different things. By provable, I meant the user has a proof that his transaction has now been registered at a certain point. It's also provable in the sense that I have math proofs for all this stuff, and if you go to our website, you can read my math proofs, like Byzantine fault tolerance, those sorts of things. So we have interesting properties that we get by having just this graph, this hash graph, instead of having a single sequence, a single chain of blocks. How does it work? And I have all of 8 to 12 minutes to tell you how it works, which is good because the entire algorithm fits on one slide. In fact, the entire algorithm fits in one sentence. And so I have one slide left, basically, in this presentation to show you how Hashgraph works. So it's kind of fun to go through it. Here is how Hashgraph works. So here's how the Swirlds consensus algorithm works with the Hashgraph. The first concept is gossip. A gossip protocol just means you have a bunch of computers, and each computer randomly picks another one of the computers in the community and tells it everything they know. So Alice randomly picks Bob and tells Bob everything she knows, and then maybe Bob turns around and tells Alice everything he knows. And then Alice picks someone else at random, maybe Dave, and she tells Dave everything she knows. And she just keeps doing this. Gossip protocols are used all over the place. They're used in blockchain. They're very old. And the nice thing about a gossip protocol is that there's no central guy in control. There's no central server. It's very reliable because of that. If a few nodes go down, it still works. And the information spreads fast. I mean, you know, how fast is the grapevine in some organization? Yeah. Sometimes it's so efficient that the rumor gets out before the thing that it's about happened. So let me just show you a picture of a gossip protocol. And gossip is you tell two friends who tell two friends who tell two friends, and before you know it, exponentially fast, the whole world knows. Here's a picture of a gossip protocol. Each column is one of the participants. Each circle is a gossip event. Each circle represents an event where someone gossiped to someone else. So for example, the top circle, and time goes uphill. We start at the bottom and we work our way up. We're growing like a tree. At the top, that circle is in the Bob column. So this is the event of somebody gossiping to Bob and giving Bob everything they know about whatever it is we're gossiping about. Now, who gossiped to Bob? Oh, look at the line coming down from that. It goes to Carol. I guess it was Carol who gossiped to Bob and told Bob everything she knew at that point. And if you're wondering which version of Carol's knowledge base it was, well, you can see which circle that line connects to. That tells you it's what Carol knew at that point in time. That's what Carol told Bob. So this is a picture that applies to every gossip protocol. It applies to gossiping about identities. It would apply to gossiping about transactions. It would apply to gossiping about mind blocks. It's used throughout computer science. Everybody has things that this would be a picture of gossiping about different things. But what if we were to gossip about gossip? What if we were to gossip that picture? Instead of me telling you all the identities I know or all the blocks I know, what if I were to tell you all the pieces of that picture that I know that you don't know? In other words, this isn't just a diagram of how we're gossiping. This is actually a data structure in your computer, and it's the thing we're gossiping. That's very weird. So we're going to gossip about gossip. I'm not just going to tell you the latest juicy rumor. I'm going to tell you who I heard it from, and who they heard it from, and who they heard it from, and going back forever. And so each of these circles now is actually a little sequence of bytes. That top circle there is an event that Bob created on his computer. It's a sequence of bytes that Bob created. It contains the hashes of two other circles, the two below it that it connects to. So it has a cryptographic hash of Bob's previous event, the last one he created before this one. Check. Interesting. Okay.
Check. Oh, dude, this is beautiful.
That's gossip. My microphone is gossiping on its own. See the power of gossip?
1, 2.
Okay, so that top circle contains within itself two hashes. The hash of the circle right below it and the hash of the circle to the right.
RF analyzer.
Each event contains within it two events, and Bob is just saying, with one of those hashes, he's saying, well, here's the previous hash of mine, so that Bob's personal hashes or events form a chain. And here's the one from Carol, which is his way of saying, Carol just told me everything she knows. So it just has those two hashes inside of it. And also, if we do need transactions somehow, so what we'll do is we'll stuff them inside the event also. So any transactions that Bob feels like creating at this moment, because he wants to start a session or spend some money or whatever, he'll put them inside the circle too. If he has no transactions, he'll just leave it empty. That's fine. So Bob's event is going to contain whatever transactions he wants, if any, and two hashes, and then he digitally signs it. So it's this eternal proof that at that moment in time, he knew everything Carol knew.
Check 1,
at least
2,
everything
check,
that comes
check,
as
1, 2, check,
an
1,
ancestor
2,
below that circle on the right.
2, check.
And that he is the one who did it.
Check.
And so that's it. That's actually incredibly efficient. You know, if we were just going to gossip transactions, not even worry about consensus, then we would still have to send everybody the transactions as they happen and gossip them around.
1, 2.
We'd use up bandwidth for that.
2.
And we'd still have to sign each transaction, so the signatures would still be there. So the only overhead we're adding are the two hashes. But wait, turns out I'm never going to give somebody one of these circles until I've already given them the two circles below it. So that top circle, when I gossip that to somebody, I don't have to actually give them the two hashes. I can just somehow describe to them this circle and that circle, like an identification number for those two circles, and they can look up the hashes because they already know them. So I don't even have to send the hashes over the internet. All I have to do is send over the internet the signed transaction that I was already going to send anyway, plus just a few bytes to tell them an ID number for that guy and an ID number for that guy, and that's it. Very little overhead. So the simplest thing I could imagine is I just gossip transactions, and that takes, I get no consensus, but everybody ends up learning the transactions. If you want to gossip the hash graph, it's just an incredibly tiny amount of extra bandwidth on top of that. And then everybody has the hash graph. Great. So we're going to gossip about gossip.
Check 1, 2.
but we still don't
Check
have
1, 2.
consensus. The nice thing about blockchain is you have a chain of blocks. I know what order things go in. They go in the order of the chain. But here, I have this strange picture of circles and lines. In math, we would call that a graph. And each vertex in the
Check
graph
1, 2.
has within
Hey,
itself, in
1,
cryptography,
2.
we call them hashes. So it is a hash graph. So in the hash graph, you can't look at it and say, hey, what order are these guys in? I can tell when there's a line that this came later than that
Check
one,
1,
which
2.
came later
Hey, hey.
than that one, because
1,
there's
2.
lines between them. But I can't really tell two siblings up here which one came first. Oh, no. So how are we going to get consensus? Well, the answer, I'm sorry? Vote for it. So this is the traditional answer. For Byzantine fault tolerance, we have rounds of voting, and they can be order in squared, where I tell everyone my vote, and then everyone tells everyone else a receipt on my vote, or even in cubed. Mine is not order in squared. It is not order 1. It is order 0. We do virtual voting that involves no votes. Whoa. Here's the key. Yeah, that would be good. Now, the problem is that we all have to believe the same thing for this to work. I'm not sure that happens in US elections. Now, the key here is that this diagram isn't just arbitrary data. It is a record of a gossip protocol. Everybody ends up with the same picture. This picture here, this graph, is always growing upwards. When a new event is created, it propagates at the speed of gossip through the community. And very rapidly, the whole community knows that circle and everything below it in this graph. And so very quickly, we all get the same picture of this graph. And then you could say, well, I could run any deterministic algorithm on this to turn it into a total order. Just any algorithm. And if everybody's running the same algorithm, everybody will get the same order. We're done with no voting. And there's some details that are tricky, but you can get around them, but that's
Check
basically
1,
it.
2.
And so what you basically do is you run one of these traditional Byzantine algorithms in a sense, but all the voting happens in your mind. Alice says, if we were
1,
running this
2.
protocol, at this point in time,
Check 1, 2.
how would Bob have voted if he had been voting
Check
to
1,
me?
2.
Oh, well, I know everything
2.
Bob knew at that point. I know exactly how the
Hey,
protocol
1,
says Bob
2.
should have voted. So I'll just calculate what
Check
his vote
1,
was and
2.
pretend he sent me that vote. That's it. And we're done. You have mathematically guaranteed Byzantine fault tolerance, which I haven't even defined, but it
Hey,
means
1,
it
2.
works.
Nice. Check 1, 2. Hey, hey. Hey. Check 1, 2.
Exactly. Exactly.
Check,
Sorry to
check.
get too technical
1, 2.
there. Byzantine works. That's the math definition of it. But we get all those properties for free with zero additional communication going back and forth other than just gossiping the hash graph itself. And gossiping the hash graph itself
Check,
is
1, 2.
almost no
Check,
bandwidth
check.
over just
1,
gossiping
2.
the transactions themselves. And if I want everyone to know every transaction, you can't get less bandwidth than that. Everybody has to hear every transaction and pass it on average to one other person. And so we are almost at the exact mathematical limit of how much bandwidth you could get away with for low bandwidth, and then nothing beyond that for the consensus part. You just get that for free. Not only that, the hash graph lets you reason. Alice knows what Bob knows at each point in time. In fact, Alice not even knows what Bob knows about what Carol knows. And she knows what Bob knows about what Carol knows about what Dave knows. You can do these long chains of reasoning, which allow you to do some really interesting optimizations in your voting algorithms, which is very convenient. In addition to that, we automatically get receipts. If there's a node from Bob up there that has the hashes, everything below it, we know that Bob saw everything below it. He digitally signed it, and because of the nature of cryptographic hashes, we know for sure that he really did know everything below it in the diagram. And so we have proof of receipt. And not only that, it's very, very easy, once you're putting these in order, for the community to come up with a timestamp. Basically, everyone is essentially voting on when they think that they received this event. And then it's the median of all those times. So we get for free almost virtual voting on the exact time at which the community received each event. And so now we have provable, digitally signed community consensus on the ordering of the events, on the exact timestamp for each event, and it's all digitally signed. We can end up with states that are digitally signed and a history, and it's immutable. So that's Hashgraph. We have a 23-long-page tome on our website you can download that has all my math proofs of this stuff. But I hope you found it entertaining. I found this kind of fun to play with. And very soon there'll be an SDK on our website. If you wanted to, come back at 4:20 in this room in a half hour, and I will give an hour-long talk on how to build apps on top of the platform that use this thing. And it talks about the architecture, too. So if you're interested in what would it look like to build an app that uses distributed consensus, come back then. Thank you. I was bad and went 18 seconds over. Do we have time for a question or not?
Let's just take one question and then
Okay,
perhaps reserve the rest for the workshop later on.
So, Leemon, thanks very much for that. You said early on that this is not permissioned. Is there any reason that it must not be permissioned?
No. I'm sorry. You can be permissioned. You are allowed to give this to people you trust. You don't have to give it to people you don't know. Yes. That's actually an excellent question. I misspoke there. I'm just saying there are some algorithms where it's so fragile you have to trust everybody. But if you trust everybody, why don't you just have a server? Okay. So I was just saying we don't have to do that. And I'm sorry we don't have time for more questions, but I'll be here for the next 10 minutes. Just come up and ask. Thank you.